currently have a live chat going, so you guys can ask us questions while we are going through this. So if any of you feel like you're confused, by all means, feel free to let us know, and we will try to see if we can address it while we're going through this material. So, just to get things moving along, the topics that we'll be covering today are, again, we're going to kind of revisit the problems that exist in machine learning. We're going to address this problem of shift invariance, which basically means you want your algorithm to work even if you shift the signal a little bit in time, forward or backward. And we're going to kind of readdress this issue of biosignals and kind of dig a little bit deeper into really what this means and what kind of concerns you have to address and how we go about resolving that using what's called preprocessing. So we're going to address noise concerns, some basics of digital signal processing. We're not really going to get into like the theory so much as the way in which it is practiced. And then we're going to talk a little bit about signal composition, feature transforms, frequency transforms, and some easy to use and popular features, as well as addressing feature and class dimensionality. So, to kind of proceed a little bit further, so kind of revisiting how we go about doing machine learning. So this is an example with EEG signals where you select a given channel of EEG, you pre-process it, then you extract the features, you select those features that you want out of the features that you've extracted, and then you train the algorithm and test the algorithm. So to kind of approach this kind of problem of like how we go about training this algorithm, we kind of have to consider two different aspects. There's overfitting and there's underfitting, which ultimately consists of a trade-off between bias and variance. Some things that will affect your ability to have good quality machine learning algorithms include your accuracy of your recording, how consistent you record that way, whether or not your data acquisition hardware is of good quality, if your noise reduction is proper, if you have good common mode rejection, and if you're recording all of the signals that you need to make your classification. Now, in some cases, there are multiple ways to get to the same solution, and so there are many different papers out there that solve the same problem multiple different ways. So, for the most part, it's good practice to be able to kind of go into a lot of the literature on whatever machine learning algorithm it is that you're looking to implement. So, another problem that will come up is this idea of dimensionality. So if you have very high dimensional data in your data set, in other words, you have a lot of data, then in some cases this can make your algorithm ridiculously slow, or slow enough that it's not feasible to do what you're trying to do. So a good example of this is if you need a high reaction time for something, and your algorithm takes several seconds to be able to respond, that may not be fast enough. So in that case, you need to reduce the dimensionality of your data so that your algorithm will be able to run fast enough. On the other hand, you can run into the same sorts of problems with classes and features, in that if you have too many features, your algorithm may overfit because it thinks that it's looking for something that doesn't actually there in the pattern of the signals. Another thing is if you have too many classes, you're going to run into a variance problem where you have to have absurd amounts of data. So now you have this trade-off between all three of these different sets: classes, features, and the amount of data that you have. So what this ultimately comes down to is a classification of speed versus scalability and variance and bias again. So as you can see, bias and variance kind of pervades this whole problem of machine learning. And another note is the length of time you record a signal also affects this because it increases, first of all, the dimensionality of the data that goes into your algorithm, but also the length of time you record affects how high resolution you can get on your frequency transforms. And we'll talk a little bit about that. So what do you think is going to happen if you give an algorithm only perfectly synchronized data always at exactly the time of the event key press? It will not work well real time, unless you can somehow guarantee that the data being interpreted is always correctly synced. In other words, let's say I'm looking for an ECG, right? Then I would need to guarantee that every ECG signal I record from a patient in the live setting is 100% synchronized to the exact position of when the QRS wave is and when all the other waves are. And this doesn't really make sense, especially when you consider arrhythmias, for example, where people have different beat shapes, or for instance, if their QRS is improperly shaped, or other issues that can come out when you're looking at ECGs. So as a result, this really doesn't make much sense to do for real time. If you want to be able to classify a real-time event, even if it's shifted a little bit forward or a little bit backward in time, you need to take this and basically shift the signal forward and backward. So I'm going to kind of show you an example of this kind of visually. So you can see behind me here, this is an example of like one event that's occurring in a single signal. It's circled in red. And you can see I've drawn arrows to the left and right here. Basically, the gist is you take this signal and then you shift it forward and backward in time. Now, how you do this is you record for longer than the length of this signal, and you have a little bit of space before when the signal occurred that you can also include. So that way, you can take the signal and basically chunk it before when the event occurs, but make sure the event is still within that slice, and also shifting it forward to just after when the event occurred. As a result, this temporal change, or change in time, that will happen over the course of the signal can be accounted for, and so you shouldn't get as low accuracy when you try to perform classification if you include a bunch of shifted samples. The problem is that it does matter how big this shift forward and backward is and how many of these shifts you have to the forward and backward direction. Sometimes you may want more forward, sometimes you may want more backward. It depends on your problem and the context of the example. But in this particular case, something that I would want you to consider is this idea of localization error. So this is kind of a word I've come up with for how I describe this. And basically the way it works is if I have a signal, for instance, with this kind of oscillatory component, and then it goes straight over here, and I think the event happens here, right, when it shifts, then if I don't capture the frequency components that are changing between these two things, then I may not end up with a good classification accuracy. So, for example, let's say I have a signal that is just a step response, right? But overlay on top of it, we have a big spike. And maybe this spike is actually important to recognizing the signal. If our shifts are such that we think this is when the event occurs, and we shift to here and to here, we don't see this signal. This gets completely missed. And so the problem is that we cannot actually identify this particular aspect of the signal, and there's no way for us to be able to know whether or not our signal is classifying based on the quality of our data, or if it's because it's not properly shifted. So the only way you can do this is you can test different values of this distance, and you can actually use different distances for your shifts if you wanted to. You don't have to use equal distance shifts. But you can also choose to have more shifts forward or backward. And in doing so, you can capture more features that are over here if you think there's like an oscillatory component that maybe is after when the event occurs, or maybe a little bit before. In either case, you can use this shifting method to approach this shift invariance problem that you run into with machine learning. So kind of returning back to our original conversation, so we've kind of addressed this idea of shift invariance. Over here on the right, you can see another example of this. This is actually with some EEG signals that I've recorded, and I've taken that signal and shifted it in time forward and backward. So you can see right here, this is an example of me shifting this signal here forward, and then another example here, you can see of me shifting this green signal backwards. So basically, the gist is you make a bunch of copies of this, and you include all of those copies in your algorithm for its initial training and also for its testing. So again, kind of returning back to the problem of biosignals. So remember, they're very, very small. So because these signals are so small, they're susceptible to noise problems. So you need to make sure that you observe this signal with a high signal-to-noise ratio. So you have to have good common mode rejection is what it's called, which means that any signals that are in the area around where you're recording but aren't the signal that you want need to be removed from the signal. So there are kind of a couple of ways we can approach this, but one of the more common ways to approach this problem is to use filters. So the wall that you connect, like a large plug that basically powers some of our more common devices we have in the lab, that wall is powered by 60 hertz AC power. So the thing is, that signal can sometimes be picked up on some of your signal recording devices. And this can even happen also due to the lights in your room, and that can create another source of noise. But the problem with the lights is that those aren't necessarily going to be at 60 hertz. You have to know what kind of light is in the room that you're working in to even know what frequency of noise you're going to be getting from that light. Nonetheless, there are certain approaches that are taken when trying to approach this kind of problem of filtering. And you can do this in hardware or in software. So there's what's called a low-pass filter. So you only include frequencies below a specific frequency, and then any frequencies above that are significantly reduced in magnitude. So they don't disappear exactly, they just get smaller. So this is actually important, especially in hardware, because if you make like a first order filter, it's not going to reduce the signal that much. But if you make like a fourth order sync filter, for example, then you could significantly reduce any signals that are not what you're interested in. And as a result, you'll get a much higher quality signal. So the number or order of your signal becomes a lot, of your filter becomes a lot more important in hardware. So another thing to think about is bandpass filters are basically a combination of a high-pass and a low-pass filter, and a band stop is basically the opposite of that. Instead, you're removing things in a specific region of your signal between one frequency and another. So there are a couple of different types of filters, but some of the more commonly known ones are Butterworth, Chebyshev, elliptic, and effectively, Butterworth is a maximally flat response. You're going to get a flat kind of frequency gain in the region that you choose to allow to pass. So, low pass, you let low frequencies pass. And then anything outside of that region gets reduced, but not quite as quickly as, for example, a Chebyshev filter. The thing about a Chebyshev filter is that there's often ringing in the pass band, which is what we refer to when we talk about the bands that are allowed to pass. And outside of that region sometimes as well in certain filters. So to kind of go a little bit further, you can see kind of an example of poor stop band attenuation happening in an analog filter. So this is like a hardware filter, like you built like a circuit, and it didn't really attenuate the signal that much. But in a digital filter, they often are much better at removing a lot of the like unneeded frequencies because of their ability to be more. You don't have to worry about the inaccuracies that can be associated with specific components, for example, with analog filters. So on the left, you can see an example of a moving average filter. This is kind of a different approach. Instead of using like a filter function, what you do instead is you take an average of a number of data points as they come in from your device. And in doing so, this effectively acts as a low-pass filter. And so you can actually choose to, instead of just taking a direct average, you can weight certain particular samples that you record more so than others. And in doing so, you can create what's called an infinite impulse response filter, or an IIR filter. This example is shown below in this little exponential weights thing here. And kind of more detailed explanations of this you can kind of find online. But the general gist is you take the same signal that you've recorded over, let's say, 5 times you've taken a sample of this signal, and then you take an average of those 5. And you can, instead of taking an average, you could say each of those samples is multiplied by some number, and those numbers are called weights. And then you divide the sum of all of these numbers multiplied by their weights by the sum of the weights. And in doing so, you end up with effectively a weighted average of those signal samples. Now, another thing to remember is once you've recorded the signal from your analog device, the maximum signal you are able to correctly identify from your signal, in other words, the maximum frequency you can see, is half of your sampling rate. So if I record at, say, 500 hertz, the highest frequency I can reasonably observe is 250 hertz. But even then, the signal is not going to be very clearly observed. It is highly recommended that when you are trying to record a given signal at, let's say, 100 hertz, you should always record at least 10 times that rate. So if I have a 100 hertz signal, you should be recording at 1,000 hertz. As a result, you'll be able to much more clearly see the signal you are trying to look at. So you can see here, this is kind of like an example of what happens if your sampling rate is not high enough. So over here on the right, you can see this person is clearly not sampling fast enough. As a result, the signal that they're looking at looks like a lower frequency. And so this is why in your fast Fourier transform, you'll actually end up seeing a lot of higher magnitudes at that lower frequency, even though the signal you're actually looking at is at a higher frequency. And this is what is called signal aliasing. Another thing is, this fast Fourier transform can be used to identify the magnitude of certain frequencies in your signal. So the far left in your fast Fourier transform is going to represent DC, or non-changing values. So this is an example of DC here. And then on the right, everything off to the right of that is going to be your oscillating, your different frequencies above 0 hertz. And this is an example here on the right. And you can see that this here is being done at approximately 10 times the rate of the signal for the sampling rate. And so as a result, they are able to correctly recreate the signal from these samples. So this is why it's very important to consider the rate at which you are sampling and the signals that you are trying to look at, what frequencies they are at. Another thing to think about is how long do you need to record before your classification algorithm makes a classification. Well, if one of your features happens to be the fast Fourier transform, the length of time affects the resolution you get. So you can see here there's this equation here of resolution. This is your maximum frequency, which is half of the sampling rate, and it's divided by the number of spectral lines you get. The number of spectral lines is equal to n over 2, where n is the block size, or the number of samples that you've recorded. So let's say I record 100 samples. Then that means n is 100, so spectral lines I get is 50. So then we have 50 here under the maximum frequency. If I recorded at 500 hertz, then the maximum frequency bucket is 10. So you don't get very much resolution with that. Most people want to get like somewhere on the order of like 1 hertz frequency resolution. In some cases, it's not necessarily feasible. So in some cases, if you want to be able to record fast enough, you have to reduce your frequency resolution, or you have to increase your sampling rate. And so this was kind of the problem I wanted to address here. If you want a little bit more detail about how to apply this, I highly recommend you go through some fast Fourier transform tutorials. And there is a great kind of example that was given by another person. His name is 3 Blue, 1 Brown, I believe. And he gives a great tutorial on how fast Fourier transforms work. So this is kind of another example of the fast Fourier transform. So if I'm recording, for example, 8,192 samples, I have to divide that by 2, and I get 4,096 fast Fourier transform bins. And so if I divide a signal that I am sampling at 10 kilohertz by 2, I get 5 kilohertz, and that is the maximum frequency we can observe. If we divide that by the number of fast Fourier transform bins we get, we can determine the number of the amount of the frequencies within a certain range we can observe within any given bin. So the first bin would be from 0 to 1.22 hertz. The second would be from 1.22 to 2.44 hertz, and so on. So basically what this comes down to is there's always a trade-off between temporal resolution and frequency resolution. In some cases, it may be okay to record for a longer period of time because maybe you don't need to respond as fast. In some cases, you need to respond more quickly, so it's okay to have a lower frequency resolution, assuming you can classify it accurately with that resolution. So I kind of mentioned before this idea of aliasing and the kind of sampling rate being at least 10 times the highest frequency of interest. This is very important, and we kind of saw an example of this earlier. Basically what it comes down to is you need to perform your experiment and look at your FFT and look at how your algorithm is performing and use that to make a decision about how you want to proceed. But another way you can approach this problem is to use faster sampling rates, so basically get a higher sampling rate device, or using filters that can adjust for some of these problems at the analog level. So you'd have to build a hardware solution for some of these signals that are getting aliased into your fast Fourier transform if you want to properly filter them out. But another issue is that you could keep doing this forever, right? Like you could keep increasing your sampling rate ad infinitum, and eventually you'll find that, you know, maybe I'm not finding as much useful information out of this anymore. So really what it comes down to, at least for practical applications, is this useful at the rate at which we're currently sampling? Do we need to increase it? If we need to increase it, you can try to approach it that way. If you get better results, then that may be a sign that there is higher frequency information you may want to be paying attention to. But that's not always going to be the case. So this is kind of an example of this when we're working with the OpenBCI device. So I'd like you to kind of like think about this. I'm going to give you about 2 seconds to think about it before I kind of give you the answer. But for the OpenBCI, without the Wi-Fi attachment, the highest frequency, what is it that you can observe when you're sampling at 250 hertz? What is the resolution of those frequency bands? So I'm just going to kind of give you a second. So, based on our assumption of 0.4 seconds of data recorded, the following is the answer to the question. So, basically, you end up with half of the sampling rate, 125 hertz, is the highest frequency you can observe in this signal. And kind of going back to the amount of the data that we recorded 250 samples per second at 0.4 seconds of our signal. That gives us 100 samples. So we've recorded the data on all of our EEG channels, let's say, 100 times. So Now we have 100 divided by 2 FFT bins. That's 50 FFT bins. So if we divide 125 hertz by 50 bins, we get 2.5 hertz per bin. And so that is our frequency transform resolution. So this is kind of an example of like what you might see in a fast Fourier transform. So what you can see over here, this is an example of a 2 hertz sine waves or a cosine wave signal. And this is a 3 hertz sinusoid signal. And these two sinusoids are being added together to produce the signal you see below. And you can see that the fast Fourier transform looks something like a sum between the fast Fourier transforms of the previous two signals. And partially this is because the fast Fourier transform is showing you the frequency content at the frequencies of both of those signals. Now, kind of what the fast Fourier transform looks like more from like an analytical standpoint is something like an integral like this. And there's a guy, as I mentioned, 3 Blue, 1 Brown, who does a really good job of explaining this, and I highly recommend you watch his YouTube video if you have not already. So this is another example of that, kind of with a longer signal. So what you can see here in this signal is an example of a signal that has been DC shifted. So in this case, you'll actually see that there is a big spike at the beginning of your fast Fourier transform. This is due to the shift of your signal up from 0. So this is partially why a lot of times when you take the fast Fourier transform, because you may want to see some of these lower frequencies, you're going to want to do what's called mean shifting. So you take the average of the signal that you have been trying to take the fast Fourier transform of, and then you subtract the average from all of the data points, and you shift this down. So let's kind of move away from the fast Fourier transform for a little while, and let's kind of dig a little bit deeper into feature extraction and talk about like what kind of features you can use. Now, the vast majority of the features here are not really going to be very useful in most applications, because a lot of the time you end up taking the signal and you end up scaling it between the minimum and the maximum anyway in order to perform feature scaling. So things like the minimum and maximum and the like skewness and kurtosis may not necessarily work, especially if you use my shift invariance approach that I showed you earlier. Part of the reason for that is that you record the signal at skews to either side, so the skewness may not be useful to you at all. But the variance and sometimes the average value can still prove useful, as well as the standard deviation. More useful, on the other hand, are things like averaged fast Fourier transform buckets. So basically you take a couple of those bands, and then you take the average of them, or you can take the weighted average of a couple of them across a couple of those different frequency bands. Another thing you can do is you can take all of those frequencies, and you can perform a weighted average. You see, the weighted averages, they work their way into all of these things. But generally, the gist is you take a couple of those frequencies across some range. So in this case, let's say our fast Fourier transform is from 0 to 125 hertz, like in the OpenBCI. Then you can take, let's say, from 0 to 125, and you multiply each of those bands' frequencies by their magnitude, and you sum them together and then divide them by all of those magnitudes, and you get what's called the average frequency. And that average frequency can give you some meaningful information about what is most active during that particular part of the recording. So another type of feature that you can extract is what's called the Hjorth parameters. The Hjorth parameters have gotten a lot of traction in recent years as a useful signal for biosignal analysis. However, in more recent years, in like the past year or two, there have been more useful features such as the power spectral density, or PSD, and the Empirical Mode Decomposition, or EMD, that have been becoming more popular for use in this space. But the Hjorth parameters are actually still quite useful and have been very commonly used in speech and language analysis for things like hidden Markov models. So you can see here an example of the mobility and complexity of a PPG signal. Now, I didn't explain this last time because we kind of were a little bit short on time, and I wanted to focus on things that we would be talking about in our lab. But the PPG, or photoplethysmography, is effectively going to be able to show you your heart rate, so you can kind of see the pulsation of oxygenated and deoxygenated blood by shooting a light at your blood vessels and then having that either reflect or be read through the finger. And so that's what that like device that you put on when you go into a doctor's office over your finger that they record your heart rate on, that's exactly what they're doing, is they're performing PPG. Now, when you see the PO2, the percent oxygen thing, you can't do that unless you have 2 PPGs. But we're not really going to get too deep into that because it's not kind of not the focus of today's topic. I just wanted you to understand what kind of signal you're looking at here in the lower right corner. But you can see that what they're trying to do here is they're looking for artifacts, and you can see all this noise in this kind of region here. They wanted to know when that was. So this particular experiment was a group of people, they were trying to do artifact identification in PPG signals. And in doing so, they were able to use the Hjorth parameters to correctly identify that. So the other example of a feature that we could potentially use is called the power spectral density, or PSD. And basically what you're doing in this case is you take the signal and you can decompose it into something similar to the fast Fourier transform, but not exactly the same. It effectively uses like squared signals rather than the base signal. And it actually turns out to be quite useful for EEG analysis. In fact, the BCI Competition 3 Set 5 data set actually uses PSD as their pre-extracted features, and you can get pretty high accuracy using just that. So, again, the fast Fourier transform, we kind of talked about a little bit what it was, and I think it's kind of worthwhile to mention that a lot of times when people talk about the power spectral density, they kind of describe it as an approximation, or rather, they should say the fast Fourier transform is described as an approximation of the PSD. As it is effectively defined discretely in software as the function that you can see here. So this is kind of similarly based upon the fast Fourier transform, and there are a wide variety of other feature extraction types. Now, I don't know that there have been any questions that have been coming up, so I'm just going to kind of proceed. So kind of moving onward, I'm going to talk about this thing called empirical mode decomposition. So in general, your signal can be comprised of a number of other smaller signals all combined together. And this can be basically described as what's called these intrinsic mode functions. So you can use empirical mode decomposition to take your signal and tear it apart into all of these, what are these called IMFs. And these IMFs can be used to get information about how your signal's frequency space changes with time. So to kind of show you an example of this, on the right you can see this is a sine wave signal that was kind of decomposed into its intrinsic mode functions, showing how they change over time in their frequencies that are present. And then you can see on the left here, this is an example of the energy at specific frequencies over time of that same sine wave signal, to kind of give you an example of like what you might expect to see from doing the Hilbert-Huang transform with empirical mode decomposition. So, kind of going back to this whole problem with feature extraction from like a more generic standpoint, you always must feature scale. If you do not feature scale, your algorithm may still learn, but the features that you record that have a larger magnitude may end up taking a larger weight in your analysis, and so your machine learning algorithm may not correctly train itself on the data that you've provided it. So if you want your algorithm to give equal weight to all of the parameters that it is taking in when it is first processing it, you must scale them all comparatively. Now, another problem you may run into with this is that your features, when they've been scaled, may have different distributions. So some of them may be more shifted towards the lower values of those features. And it's possible they may be linked towards the higher end of those features as well. So you can kind of approach this using what's called a Box-Cox or a Johnson transform. I'm not going to kind of get into the details of this, but the gist is that the Johnson transform can handle much more complicated forms of these distributions to basically change them from the current distribution to something more similar to a normal distribution. So we kind of talked about this a little bit before, the eternal problem of machine learning with overfitting and underfitting. You need to make sure you approach this, and you need to make sure that you consider whether your algorithm is overfitting or underfitting. Generally, if you fix one, the other gets worse. We kind of talked about this a little bit more in the previous video, so I'm not going to focus on it much anymore. But I'm going to kind of dig a little bit more into the feature dimensionality aspect and how this relates to that. So the thing is, if you have a lot of features, you can end up with a really high variance unless you record a lot of data, or you can end up with overfitting to those specific features, and that causes problems with your algorithm. It can also make your algorithm much slower to train and to run. So in general, you don't want features that are not necessary for your algorithm to run. You only want the data that you need. So it's important to make sure that you select the features that are necessary for your algorithm so you don't reduce your algorithm's efficiency and performance unnecessarily. Another thing is if you don't have enough features, that's still an equally problematic issue, because you now run into a high bias problem where you're now underfitting and you're not seeing all of the details of the signal. This is the same thing as what we were talking about before with this kind of shift invariance problem, where if you jump too far away, you miss the localized features. So the advantage, though, to having fewer features is your algorithm will be faster to train and to run. It just may not be accurate. So another thing to think about is making sure that your features are good. Good features reduce your bias, and if they are collected over a large enough sample size, it also reduces variance. So the thing is, the features themselves are not what's reducing the variance in this case. It just so happens that the variance of your model is going to be reduced as a result of you collecting enough data of a good feature. It's not going to actually improve your algorithm if you have a bad feature, so you'll see that removing those bad features may actually improve your accuracy or not significantly reduce your accuracy. So like 2% is a good measure, for instance. Like let's say I have 98% accuracy, I remove one feature, and it brings my accuracy down to like 96%. That's not really that much of an important feature. Maybe there's a better feature that brings me up to 99%. So it's possible that you may want to investigate other features. That said, though, if it does improve the accuracy of your algorithm, both on the test and the training set, you don't want to just remove it. You may want to include it, even if your feature selection says it's not needed to get the high level of accuracy, because it still improves the accuracy of your algorithm. So you can see that to some extent this is a bit of an art and not exactly so much a science in some cases. You kind of have to play around with it and figure out what works best for the given problem that you're working on. So a little bit of a side note on neural networks, because I know a lot of you guys are really interested in those. So something that's kind of important to remember about neural networks is that they do not function using combination effects. So if you have a feature A and a feature B, and you want to include the interaction between A and B as A times B, you need to create another feature which is A times B. You can't just make a neural network that creates those combinations of features, because it may not just be a linear combination. It may be a nonlinear function. And so while the neural network can potentially model nonlinear functions, you need to actually change the way that your features are being input into the network, and you need to understand what is actually happening in the network to make sure that it is actually able to model that. And so it's important to remember that if you want interactions, you need to try out those interactions as features to make sure that you're not missing out on some dimensionality or missing out on some aspect of the complexity of your model and ending up with a high bias as a result. So let's kind of address this problem of feature dimensionality using what's called feature reduction. So something that may make kind of more obvious sense to you is, let's say I have 50 features. I try removing every single feature once and see which one increases my accuracy or reduces it the least. And I do that one at a time, over and over and over again until I'm happy. The alternative is I start with no features, I add one, and I try out all the features and figure out which one gives me the most improvement in accuracy. And I do those iteratively. There are plenty of algorithmic approaches to doing this, but this is just like one example that's fairly commonly used. But you can also use a couple of other methods. So one example of this is the brute force method. You literally put all of your features into what's called a brute force a neighborhood component analysis. And the neighborhood component analysis can be used to basically identify which features have the most weight of importance to your model. And so in doing so, you can choose to remove the features that are less important based on a threshold that you can set. Now, I personally like to do that based on the variance of those examples on each run of the neighborhood component analysis, because when you run NCA, because there's a little bit of randomness involved in running it, your results may differ between runs. So it's important to run multiple times the neighborhood components analysis, so you know for sure that what you're looking at actually makes sense as the weights for your features. So in doing so, though, you end up running this algorithm for a very long time. So if you have on the order of 144 features and like 20,000 examples, expect this algorithm to run for 5 hours. So another thing is you could also just do direct statistical analysis of your data. You could literally take every example that you have, or take one example of each type of data, and look at it statistically, see all right, which ones have more of this feature or less of this feature? And you can really identify which ones actually have significant differences. You can look at the statistical significance of that difference, and you can do more detailed manual analysis of this. There are a lot of kind of data mining tools that exist that do something sort of similar to this, but I'm not very familiar with them. So if you're interested in learning about that, I would highly recommend looking them up. Or maybe we may approach them in a future video. But for the time being, I just kind of want to leave you with this idea that you can use statistics to get this manually if you want to. So basically, the motivation to this, as I mentioned before, reducing features makes your algorithm faster, more accurate, and less likely to overfit. So back to feature division again. Remember, you want to divide the features that you take in, 75% of the data that you've taken in, as training and cross-validation, and 25% of that data goes to your test set. But the most important thing you need to remember is that you want to make sure that the proportions of data that you get of each class, and each type of each class, like if you have subtypes or anything, is equal between the test and the training set if you can manage it, if it is doable. Because the more similar the two sets are in terms of the content that they have, but the less, perhaps less similar they may be in where certain values may be, the more likely you are able to get an accurate representation of how your algorithm is likely to perform in the wild. Because the test set is supposed to be a set of data that is representative of what data you're going to actually be running this on. And the training set ideally should also be. But the thing is, the test set cannot have ever been seen by your algorithm before, so you need to be able to verify that it works on the data that it was trained on and also on the data that it hasn't seen before. And this is why this whole training and test set splitting is so important, because you need to know your algorithm will work when you take it out of the lab and you aren't using it on the same person or in the same environment, or making sure things are done exactly the way that they were done in your experiment. So I'm going to kind of show you a few examples. I think we kind of talked about this last time, but I kind of think that you may now have a little bit more context to understand what is exactly happening here. So you can see that I'm filtering out the 60 hertz frequency with this band reject filter here on the right, in the top right. And you can see down below that this is a band pass filter. I'm using a high pass to remove the DC part of my signal, as well as a low pass to remove frequencies above 100 hertz. And to kind of go back to the signal itself, this is an example recording of a blink artifact, and you can see how large in magnitude it is comparatively up here. Make sure you look at this 10 to the 4th, it's kind of important. And you look down here, and that's gone. So this signal is much smaller, and not only that, but you can kind of recognize some of the local features still in this signal, but this big wave you see, this lower frequency, is gone for the most part. Like, you can kind of see it a little bit, but it's for the most part been removed. And you can even see that in the frequency spectrum, which still has mostly the same spikes, but you can see that the magnitude of the DC component and this lower frequency range, around 3 hertz, is pretty common for blinks, for blink artifacts, and that's around like 100 decibels. But then if you go down here, now it's like 30 decibels. This has been significantly reduced comparatively. And then kind of going back to these frequency buckets, so in this particular case, an EOG example, on this particular example, I recorded fast enough that I was able to get frequency buckets between 0 and 1 hertz and do like 1 hertz buckets for each of these. But when I was working with EEG, I didn't have quite the same luxury. Now, this is, again, this feature scaling thing. So you can see here there's this skew that I was talking about, how the features have been skewed towards lower values here or towards higher values over here. Ideally, you want something more like these, which are like kind of more evenly distributed. So that way you can get more easy like splitting of the groups that you want to discriminate between. So this is an example of NCA again. So basically what we did here is we computed the error loss, or basically how much error the algorithm has for a given value of a regularization parameter. Now, I haven't really talked about regularization yet. That may be a topic for a future video, but in general, it's good to include it if your algorithm needs it. This is why we do a test beforehand to determine if your loss improves when you do a fit for your algorithm, to see if you actually need to do regularization. Because if you do, then it should help your algorithm's accuracy and prevent overfitting. And so this is an example of error loss after running my NCA multiple times. You can see, running the same algorithm, I get different results. But they're mostly kind of centered around the same value, around like 2.5% error. So this is this example of kind of feature weight and feature weight variance that I got over those 30 runs. I took the average of each run, like all together to get the weights of each of these, and then took the variance across all of the runs to see what the variance for each of these feature parameters is. And the reason why I did this was I wanted to be able to prove that these features are important, but that their importance wasn't just due to absolute chance based on the run of the NCA algorithm. So I wanted to know what the variance was so I could determine which features were more important. So in this case, I chose to use this kind of 0.4 here as my cutoff limit. So anything below here, all of these got removed from my EOG classification. And so you can see these are the features that I removed. Kind of be expected that minimum and maximum were not used because we did min-max scaling. So it makes sense that they shouldn't be important. But you can see that my fast Fourier transform buckets all were important. And this is quite common. You'll most of the time find that either your fast Fourier transform buckets or other frequency-related features tend to be particularly highly weighted in this NCA approach. And so this is an example of the accuracy I got from this algorithm using this, just to kind of justify what I'm saying, to show you we can get on the order of like 97%, 96%, 98% even accuracy when we're including reject classes to remove things that we consider artifacts. And so this is kind of showing it with PCA. So I didn't really talk about PCA too much before, but basically what principal components analysis is, or PCA, is it basically takes all of your features and creates linear combinations of it, similar to how a neural network is using weights multiplied by the different feature parameters that you're taking into it. The features that we're using in PCA analysis consist of linear combinations of the various features. And in doing so, those linear combinations become new, quote-unquote, features for your PCA space. So ordinarily you start out with, let's say, 4 features, right? And you reduce that to 2 features. So in your base frequency, or base feature space, you have a 4 feature or a 4th dimensional space. But in PCA, you see you have a 2-dimensional or a 2nd dimensional space. So basically the purpose of PCA is it reduces the dimensionality of the feature space that you're working in. And in doing so, you can make your algorithm more robust to issues, but it can also run into the problem of reducing your accuracy if you do not properly feature scale. So a good way to check if your feature scaling is working is to see, does my accuracy significantly reduce when I do PCA with the same algorithm? And if I don't do PCA, is my algorithm's accuracy higher? If it's a lot higher, like more than 10%, then that means you did not feature scale properly. Now, on the other hand, if it's not a lot, then you scaled features correctly, but it's possible your PCA may still have a slightly lower accuracy. In some cases, it could be a little bit more even. So this is an example without PCA of running it on the test data, and you can see it's still pretty accurate. And this is an example with PCA, with running it on the test data. And you can see it's still fairly accurate. It's rejecting a few more of the features, but for the most part, it's fairly accurate within like plus or minus like 5 to 10%. So here is kind of like another problem I kind of wanted to bring up, is this problem of classification dimensionality. So if you have, let's say, 20 classes that you want to differentiate between, it's going to be a lot harder to do that than classifying 4 different things. So to that end, since we know that this is true, and we can prove that this is true, we can actually show this like empirically to show that when you try to classify 4 different groups versus classifying all of their subgroups, that you'll get a higher accuracy than when doing this. It's actually possible to approach this by simply taking those many smaller classes and combining them to form superclasses of those larger groups of classes. And in doing so, you can get a higher accuracy in your classification, and your algorithm does not need to differentiate between so many different classes. In fact, you could remove some of those other possible classifications from those lower levels, but you may want to include them so that way your algorithm can go back to a previous step if it misclassified it originally. And in doing so, you know not to use that classification again, and you can determine the next classification that it's most likely to be. In doing so, your algorithm will be able to be much more robust to having extremely large classification spaces. So this is kind of an example of me doing this with EEG data. So I basically took in EEG for making 4 different positions with motor imagery, relaxing your hand, making a fist, pointing with your hand, and that last one there should not be stay, should be open. So that's basically opening your hand, and then there's reject classes. So the stays are the categories of the classes where you are staying in that position, and the transitions are when you are changing from one state into another. Now, because we have these 4 different states, and they're going to 4 other different states, we have on the order of 16 different classes, not including the reject class that you now need to classify. So this is a very highly dimensional classification space, and it can be solved much more easily by simply using a classification hierarchical approach. And in doing so, you can correctly identify which states there are with over 95% accuracy, and you can even accurately identify whether there are artifacts with 95% accuracy. The difficulty comes in identifying the transitions, which you can get at about 85% accuracy with this approach. Without using this approach, you get accuracies on the order of 70% or lower for all of these. And so it's quite clear that using this approach gives you a much better performance overall. So yeah, thank you guys for listening to my talk, and sorry for all the stuttering and all the little issues with it, but there was quite a lot of content this time around, so I hope you guys found this useful. And yeah, it was a pleasure to give you guys a little bit more information about machine learning, and we will see you guys next time.
And if you have questions, please feel free to leave them in the comment section below. We will try to answer them to the best of our ability.